and welcome honors students to Concept 1 notes in our Unit 8 solutions. And we are going to be talking about different types of solutions. Now, before we can dive into solutions, we need to review mixtures and the different types of mixtures that exist. Because if you remember from I guess it was Unit 1, Introduction to Chemistry, our Concept 3 there, we first introduced this idea. Now, in class, we're going to do a little mini lab, if you will, where we're going to explore different mixtures and, make some observations about them and that kind of thing. But for the notes, we're just going to dive right in. So I just want to remind you that there are two main categories for matter. All matter is either a substance or a mixture. So in this concept, we're really zooming in on just mixtures here. And then we can subdivide mixtures into homogeneous versus heterogeneous. And I really like these little particle diagrams here because I like how in the homogeneous mixture, it's so clear the uniform distribution of particles. See how it's so the same throughout? Whereas in a heterogeneous mixture, it is characterized by that non-uniform distribution of particles. Okay, so we're going to review this a little bit deeper. Remember, if we keep zooming in on heterogeneous mixtures, there are also subtypes of that. So all heterogeneous mixtures have an uneven distribution throughout. That prefix hetero means different, it has a different composition throughout. But there are also two kind of subcategories of heterogeneous mixtures. One are the suspensions. These are mixtures where the particles in them are so large that they will settle out unless the mixture is constantly stirred. We see this when you put oil in water, and I love this kind of diagram here that shows that. We see this in muddy water. Okay, you see this in Italian salad dressing that you got to shake it before you squirt it on your salad or else it'll just come out like completely separated. That's a suspension. This is different from another type of heterogeneous mixture known as a colloid. Colloids are the trickiest ones, y'all. They appear homogeneous or homogeneous. Think about paint. It looks completely uniform. But what we see in colloids is that the particles are in between the size of those in suspensions and solutions, which we'll get to in a minute. Suspensions have much bigger particles. Solutions are much, much, much smaller. And one of the unique ways we can identify as a colloid is by the Tyndall effect. This is when light is scattered by colloidal particles dispersed in a transparent medium. So if you were to shine a light through a solution, you would not see it. But in a colloid, you would because the different particles in it are large enough to scatter the light and make it obvious, make it visible, which hopefully you saw in our inquiry mini lab. Okay, now we've talked about heterogeneous mixtures. Now let's talk about the star of this unit, which is those homogeneous mixtures. Homo, that prefix means same. They have the same composition throughout. They have an even distribution throughout. A solution is just another term for a homogeneous mixture of two or more substances with that uniform dispersion. They're uniformly dispersed throughout. And because it has that same composition throughout, a solution has the same properties throughout, which is very important. And a solution also tends to be identified by its two parts, its solute and its solvent, as you can see. And I love this illustration here. The solute is the substance that is dissolved, and the solvent is the substance that does the dissolving. It's the dissolving medium. Okay, now let's talk about some examples of solutions because I think sometimes when we think solution, I'm guilty of this too because of what you're going to see that we're going to make in class, but we often just think, okay, the solute is like a solid and then the solvent is a liquid and we get this solution, okay? But there are so many other types of solutions. You can basically mix any kind of state of matter combination. So you can have a solution of a gas and a gas, of oxygen dissolved in nitrogen. You can have gas and liquid. Soda is really carbon dioxide dissolved in sugar water. You can have a liquid in a liquid, like alcohol in water or oil in water. When we're looking at liquid and liquid solutions, another term to know is immiscible versus miscible. Immiscible is like this picture, liquids that are not really soluble to each other and thus they form separate layers, whereas miscible is the liquids that would dissolve freely in one another in any proportion. Also, of course, we have a solid and a liquid, like dissolving sugar in water, like that lemonade powder in water. And then there are also solid and solid mixtures. If y'all remember back in Unit 4, chemical bonds, Concept 3, we talked about metallic bonds and we talked about alloys, which are mixtures of metals. Brass is simply zinc dissolved in copper. Okay, so this is possible. Typically, what we're going to be doing though is we're going to be heating them up so that they're in their liquid state, mixing them, and then, letting them cool and solidify there. Now, just to kind of review this, because this is all background stuff, like stuff we've touched on earlier in the year. This is not really new stuff. I want to do kind of like a overview, summary, review chart. Let's organize this information so we have it as a reference point, and then let's really dive into the new stuff, okay? So solutions, you should have this chart in your notes. They are homogeneous. Colloids are heterogeneous, suspensions are heterogeneous. When we're talking about the particle sizes of the components of these types of mixtures, solutions have the smallest particles, colloids have those intermediate size, and then suspensions have the largest. When we're looking at whether or not the particles will settle out, solutions should not settle out, neither should colloids, but suspensions, they will. Are you able to separate them by filtration? You should not be able to do that with a solution, easily at least, not with a colloid, but you should be able to with a suspension. And then in terms of the Tyndall effect, we should not see that happening in a solution. It should happen in a colloid, and it could happen in a suspension, but not necessarily. So again, these are not like hard and fast rules, but I just wanted to give you something really simple as a reference point, because again, this is just a review. Now we're all here. Like, this is where we're living the rest of this unit. Okay. So let's talk about solubility, because I think I've even used the term soluble since this video started, and we should probably define what that means. So solubility is a measure of how well one substance dissolves in another. And remember, this matters because that's how we make solutions. Okay, and this whole unit's about solutions. So solubility is a measure of that. Now, another definition for solubility I do want you to write. It's not going to really mean a lot to you right now, but towards the end of this concept notes, hopefully you'll have enough context for this definition to make sense. But solubility is the amount of substance required to form a saturated solution with a very specific amount of solvent at a specific temperature. And when we get to the solubility curves, this will make a lot more sense. Now, not everything will dissolve everything. Like, you can't make solutions out of everything. One kind of like rule, if you will, is the idea that like often dissolves like. That is a useful kind of rule in terms of predicting whether or not two substances will be soluble to each other. So what we tend to see by that, what I mean by like and like, is polar molecules tend to dissolve polar and nonpolar molecules tend to dissolve nonpolar molecules. But there are varying degrees of solubility. So an adjective, if for something to be soluble, we would say it's capable of being dissolved. But you can have salts that are highly soluble in water, so you can very easily dissolve them. And then you can have other salts that are only slightly soluble. They can only slightly dissolve. And so I have a little online simulation I can show you that'll give you a great visual of those differences. So not everything will dissolve everything. Not every substance will dissolve things as well as other substances. Okay, so, but there are kind of some general guidelines we can use to predict if a compound will be soluble, specifically for our purposes with water, which we're going to talk about water more in just a second. But something I want you to do is I want you to fill in this chart in your notes with these solubility guidelines. This will be helpful for you as we move forward, and you will be able to reference these. If you're my student, I will give you these on your assessment. So I'm not going to make you guys memorize these, but I do want you to write them. Okay, so example, if a compound has any of the group 1 ions, okay, like sodium, lithium, potassium, or if they have an ammonium ion, it's always soluble, period. That's like a hard and fast rule, okay? Now, if the compound has any of these anions, nitrate, acetate, chlorate, whatever, then it's also always soluble. Now, let's say a compound has, the chloride, bromide, or iodide ions, okay? If it has these ions, it's soluble except if it's with silver, copper, or lead, Okay, so it'll be soluble with anything except for these things. So if you see PbCl2, lead 2 chloride, you would predict that most likely it's not soluble, or it's not soluble. Now, I will say that one actually is soluble if the water is like very, very, very hot. That's why I say these are guidelines. I will only be asking you questions based on this. I'm not going to expect you to know like lead chloride would dissolve if it was really hot water, but this is what's going to be your template that you will use. The sulfate ion. Sulfate compounds are soluble except when combined with any of these ions, okay? And then carbonate and phosphate, they are soluble only when they're with those group 1s or ions or ammonium. Remember we said at the beginning, if it's with group 1 or ammonium, it's always soluble. That's how carbonate and phosphate are. If they're with anything else, they will not be soluble, okay? We would not mark them as aqueous before writing on a chemical reaction. We would mark them as S for solid. They would form a precipitate, okay? And then hydroxide and sulfide ions are similar. They're soluble only when with the group 1 ions, but also calcium, barium, and strontium, and then, of course, ammonium. Okay, so those are some rules. We're going to apply them practically in just a minute, but I mentioned all of these I'm talking about, are they soluble in water? Because water is considered the universal solvent. It can dissolve more substances than any other liquid. Okay, and here's why. It's polarity. Remember learning about polarity in Unit 4, chemical bonds, and talking about ionic bonds and then also intermolecular forces? Okay, water's polarity gives it this ability to create these attractive forces that can dissolve things, okay? There's also other properties of water that contribute to why it's a very versatile solvent, such as it's liquid at room temperature. If it was solid ice at room temperature, it'd be a little bit harder to dissolve things in it. It also has really high melting and boiling points compared to its size. This is because of those hydrogen bonds that are in there that's like the very strongest intermolecular force we can have. And that's related to its high specific heat. Like it takes a ton of energy in the form of heat to increase the temperature of water. That's why, again, it has these high melting boiling points. It doesn't change states of matter very easily. Okay, it takes a lot of energy to do so. This makes water really, really great at dissolving things. Now, let's talk more about dissolving things, okay? Terms that I want to make sure we can distinguish in terms of describing dissolving. Okay, so first let's define it. Let's just define the term dissolution. This is the process of dissolving in the formation of a solution, okay? And what we see when we dissolve things is that the solute will separate either into ions or molecules, and then each one is surrounded by molecules of solvent. Now, a distinct term that we see in ionic compounds is dissociation. This is the separation of an ionic compound into ions when it dissolves, okay? This is unique from a molecule. Okay, so how this happens is, think about water. It's a polar molecule. The hydrogens are less electronegative than the oxygen. The oxygen then, even though they're sharing electrons, has a stronger pull on those electrons. And so the oxygen side of water is a little bit more negative, and the hydrogen side of water is a little bit more positive. Now, obviously, in an ionic compound, it's made of ions, which are charged particles. So think about sodium chloride. The sodium has a +1 charge because it loses an electron to the chlorine, which has a -1 charge, which takes that electron. Okay, so what we'll see in dissociation is taking, this salt, those positive ends of water, the hydrogens in the water will be attracted to the negative chlorine ions in the salt. The negative ends of oxygen in the water will be attracted to the positive sodiums in the salt. That attractive force will start peeling those ions away from the crystal. Remember, ionic substances form these crystalline structures, these crystal lattices. And that attractive force between the polarity of water and the ions in the ionic compound will pull them apart from that crystal structure. And the water molecules will surround those ions. And then that's how they dissolve them. And it'll keep doing that until all or nearly all of them are separated. And this is called dissociation. That's different, though, from dissolving like a sugar molecule. Think about glucose, C6H12O6. Yes, each glucose entity, each glucose molecule, C6H12O6, will separate from the other ones, but those carbons and hydrogens and oxygens in it do not separate at all from each other. That's the difference. Everything covalent and ionic can dissolve. Only ionic compounds will dissociate. Okay? One last term to just make distinct is solvation. This is a term that I've seen in some textbooks, so I just want to make sure you saw it too. It's just talking about the interactions between the solute and solvent particles when the solute particle gets surrounded by molecules of a solvent. I just want to make sure that you had seen that because I had seen it come up too, and I didn't want you to think that's like a different thing. We're just talking about how they kind of interact with each other. Okay. So something that is unique to honors is that we're going to learn how to write net ionic equations. Okay, this is something, especially if you go on to take AP Chemistry, you will need to do, and it's not very hard. And so I want to go ahead and expose you to it now. Okay, so a net ionic equation is often written for reactions of ions in aqueous solutions instead of a chemical formula like equation would be. Okay, so we've already learned how to write equations with chemical formulas to represent a chemical reaction. So what we're saying is we're going to do it a little differently when we're talking about, aqueous solutions. We're talking about ionic substances dissolved in water and how they react with each other. Okay? So basically, we're going to show like the Cliff Notes version of the reaction. It's going to show only the compounds and ions that undergo a chemical change in the reaction because everything else gets canceled out because it's just like floating around in the solution. Okay. We call those things that are just floating around the solution spectator ions. Okay. So here's how we do it. This is one of those things where we're just going to do an example and I promise it'll make a lot more sense. Okay. So why is that? There it goes. Okay. Consider the double replacement reaction between zinc 2 nitrate and ammonium sulfide. Okay, so let's take it back, to Unit 5, chemical reactions, where we're writing all these out. So the first thing you'll do is you'll write the chemical equation. You'll use formulas, you'll use states of matter. You're going to use those solubility guidelines in that chart that we already, wrote out to determine if things are aqueous or if they would be solid precipitates. And then you'll balance the equation. Then we're going to rewrite the overall ionic equation by separating out the aqueous substances and their ions because we know that they'll dissociate in the reaction. They'll separate from each other when they're dissolved in water. Then we'll cancel out any of the spectator ions that exist on both sides, and then we'll just rewrite the net ionic equation. Okay, so let's do this one at a time. Okay, first, you got to just write the chemical equation and balance it. Okay, zinc 2 nitrate. Remember, you write the ions with their charge, and you crisscross applesauce, and then simplify if needed. So this would be zinc with a +2 charge. Nitrate is NO3 with -1. Crisscross applesauce those charges, and you get ZnNO3 2. Remember, this 2 came from the zinc. The 1 is understood. It came from up here. Now, I went ahead and wrote it as aqueous because if you go back to our solubility guidelines, you will remember that nitrate, anything with nitrate is soluble. That's how I knew that this would be aqueous in this solution without it being told to us. Okay, so we're applying those solubility guidelines here. Okay, that reaction is between zinc nitrate and, so we need a plus sign, ammonium sulfide. Okay, ammonium is NH4 with a +1 charge. Sulfide is referring to the sulfur ion, which is S with a -2. Crisscross applesauce those charges. Ammonium 2 sulfide, okay, is how you would write it out, even though the 2 comes from here. Remember, the 1 here comes from here. Now, again, I put aqueous. Look at your chart. Look at the first line in the first guideline. Anything with ammonium is going to be soluble. So I knew that was going to be aqueous, okay? Now, here's where we really throw it back to Unit 5, okay? What will this reaction form? We're going to predict the products here. This is a double displacement reaction, okay? So the cations will switch spots, or you can think of it as the anion switching spot. So zinc will now be with sulfur. Okay, so you're going to write it out. Zinc with a +2 charge, sulfur with a -2 charge. Those charges will crisscross applesauce. You'd get Zn2S2, but then you're going to reduce those to ZnS. Now, look up on your solubility chart. Okay, I don't say anything about zinc, but let's look at sulfur and the sulfur ion. It's our last rule. It says sulfur is only soluble when combined with group 1 ions, calcium, barium, strontium, or ammonium. Well, zinc is not any of those things. So that means it will not be soluble. It will not dissolve in water. It will not be aqueous. So it will be solid. Okay? That's how we're applying these solubility guidelines. Now, what else will form? Well, the ammonium ion will bond with the nitrate. Both of those have a +1 and -1 charge. So, We won't have to write anything there. And then if we look at the chart, anything with ammonium is soluble, anything with nitrate is soluble. So that's definitely soluble. NH4NO3 aqueous, okay? Last thing we have to do for this first part is balance it. So I've got 1 zinc over here, 1 zinc over here. That's good. I've got 2 nitrates, but only 1 nitrate over here. So I'll need a 2 there. Now I've got 2 ammonium ions. Well, look, now I have 2 ammonium, 1 sulfur, 1 sulfur. This is balanced. Okay, so that's your first step. You just wrote a balanced chemical equation. This is something you've been doing the last 3 or 4 units. Okay, the only difference is now you're having to determine if it's aqueous or solid using your solubility guidelines chart. Okay, that's the only new thing we've added here. You can totally do this. I'll be giving you that chart. Okay, now, next thing, I kind of just moved this up so we'd have more room. Now we're going to rewrite this as an overall ionic equation, and we're going to separate the ions. Because remember, we just said ionic compounds are going to dissociate. Okay, they'll separate. So actually, if this is zinc nitrate is aqueous, zinc 2 nitrate is aqueous, it's dissolved in water, what we're going to see is it's going to be separated out. Okay, it'll separate out as that zinc 2 plus aqueous and as that nitrate ion. And we put the 2 here in front of it instead of writing it over there, just because that's the proper way to write it once it separates out. Okay, now let's do the same thing here. These will separate because they're aqueous. So we'll have 2 of our ammonium ions and we'll have 1 of sulfur anion, okay? Now, yields. I'm running out of room, so I'm going to kind of move the products down here, okay, just for the sake of room. If I was you, I would keep going across your page. This is solid. It will not dissociate in this reaction. It will stay together. So you write it just as is. Again, I'm putting it over here just because I'm about to run out of room, okay? Now here, this is aqueous. This will dissociate. It will dissociate into 2 ammoniums and it'll dissociate into 2 nitrates. Okay? You just wrote the overall ionic equation. That's what you just did. You just did part B. Okay, now let's skip to part C. So I'm just moving this up for the sake of space. Now you're going to cancel out any of those spectator ions. Anything that's a duplicate on the reactant and product side. Okay, so for example, let's look at zinc ion. This is a zinc ion on the reactant side. Is it on the product side? Nope. So that stays. Look at this, 2 nitrates. I also see 2 nitrates in the product. So those are spectator ions. I'm going to cross them out. All right, look at the 2 ammonia. I see 2 ammonia on the other side, so I'm going to cross those out. Sulfur 2 minus, don't see it over here, so that one stays. Okay, you just canceled out the spectator ions, just the duplicates. Now you're going to rewrite the net ionic equation with what's left. I've got zinc 2 plus aqueous, I've got the sodium ion aqueous, and it's going to make this precipitate a zinc sulfide solid. That's what you did. You just wrote a net ionic equation. Hooray! Okay, again, this is one of those things I promise gets so much easier the more you do it. So for class, we're going to pause and practice this. As always, for the sake of the video, though, we're going to keep moving forward. Okay, so this concept is called types of solutions. So one of the ways that we can typify solutions is by talking about what's dissolved in them, because solutions that have ionic substances dissolved in them are different from solutions that have covalent substances dissolved in them. So now we're going to kind of differentiate between how those look differently, okay? So dissolving ionic substances. When you dissolve an ionic solute, the solute will dissociate into ions. That's what we've been talking about. Positive and negative ions separate. They move freely and independently of each other. This is that dissociation. I love this picture. It talks about what I've been talking about. Okay, so you see your sodium chloride. Remember, salts, ionic substances, they form this crystal lattice, this crystal structure. What happens is the attractive force from the polarity of water starts pulling these ions apart from this crystal chunk here. Notice sodium is a positive ion. Notice how the water surrounding it, the oxygen atoms that have that more negative charge in the polarity orient themselves around it because of that attraction. Look at the chlorine ion, which is negative. Notice how the water molecules, the hydrogens with the positive charge, orient themselves around it. Okay? We separate it out. We're going to keep doing this until every ion is fully hydrated, which we'll write down in a minute. Now, this is different from what we would see in a covalent substance being dissolved. Covalent solutes will stay as molecules. Remember, they will stay as a C6H12O6. The sugar molecules will separate from each other. Like one C6H12O6 will separate from another C6H12O6. but they do not break apart into atoms, okay? They do not dissociate. All right, that's the first big distinction between dissolving ionic substances versus covalent. Another big distinction, well, actually, this is a similarity. Ions become hydrated because they each become surrounded by water molecules that are attracted to them. So we see that, we can see how this is depicted here. Again, this is a close-up of what I showed in that last picture. Right here, look up closer. How the oxygens that are negative orient towards the positive sodium. How the chlorines that are negative have the positive hydrogens oriented towards them. We would say that these ions are hydrated when they are surrounded by water molecules. We get this hydration with covalent too, okay? Molecules become hydrated because they each become surrounded by water. Now, one distinction though, which is why I kind of have the line going this way because I have more to put on the ionic column, is a term called hydrates. Hydrates are ionic substances that form crystals with water molecules, and they have a unique notation. Okay, so for the copper 2 sulfate hydrate, you would write it as this, with this like dot kind of here. I'm not going to get into this at all with you, okay? If you take AP chemistry, we'll dive in deeper if I teach you that, okay? But for my students, I'm not worrying you about this, but I just want to give you this definition in case you see this in your textbook. If you're a student of a different teacher, you might dive into this deeper, okay? All right, one last distinction I want to make between dissolving ionic versus covalent substances. Ionic substances, when dissolved in water, can conduct electricity. We classify them as electrolytes. That's a type of solution, can be an electrolyte solution. It's when an ionic substance that dissolves in water to make a solution that can conduct an electric current. So sodium chloride can do this. Covalent substances cannot. We would typify them or classify them as non-electrolyte solutions. A substance that dissolves in water, creating a solution that cannot conduct an electric current. That's what sugar would be like. Okay, now, we can have strong versus weak electrolyte solutions though. So I want to make that additional distinction here. This is again where I have more to say for ionic than I do for covalent. So ionic substances, the strength of the ability to conduct electricity depends on how many dissolved ions it has. So a strong electrolyte solution would conduct electricity well because all or almost all of the dissolved compound would have dissociated into ions. Whereas a weak electrolyte would conduct electricity but poorly because only a small amount would have dissociated into ions. Okay? Let me show you a picture that it's going to make this make way more sense. Okay, so look at this picture. Consider a electrolyte solution that would be classified as strong. If you're going to dissolve sodium chloride in water, it's going to completely dissociate into sodium and chlorine ions. Or hopefully almost entirely dissociate. So you're going to have a ton of ions. It's going to make a strong electrolyte solution, and it's going to have a high conductivity of electricity. Now, another salt like ammonium hydroxide, when you dissolve it in water, it's not going to create as many ions as we saw here. So it would be a weak electrolyte solution. It's going to have a lower conductivity of electricity. Notice how this isn't quite as bright as this one. And then consider a non-electrolyte solution like sugar. When you dissolve sugar, notice how the molecules stay together. Notice how the atoms are not separated at all. They're individual molecules still surrounded by water, but will not conduct electricity because it's a non-electrolyte solution. Okay, I love this and how that kind of visual to summarize that. So I hope that's helpful for you. Okay. We are in class. We're going to stop and do some lab stations about solubility. Just to kind of introduce some factors that affect solubility, but now I'm just going to go ahead and tell you about it because of the video. Okay, so a few factors that affect solubility and how soluble something would be, because that's another way we can kind of describe the type of solution that it is based on how soluble it is. So the surface area of the solute makes a difference. The smaller the solute, the greater its surface area, thus the more places on it for it to come into contact with the solvent and be dissolved. Okay, so sugar cube versus granulated sugar. If you crush it up, it's going to have smaller particles with greater surface area, thus more places for solvent to come into contact. Another factor is agitation of the solution or agitating the solution. The more a mixture is stirred, the more you're going to bring fresh solvent, into the surface to come in contact with undissolved solute. If you just dump lemonade powder in water and don't stir it, some of it will naturally dissolve as it's falling down, but then some just going to pile up at the bottom because it's not going to be exposed to fresh solvent. But if you stir it, it will be. So that's another way to increase solubility. Okay, a third factor is heating the solvent. So most solutes increase in solubility with increased temperature. Okay, let's think about this. Think about our last unit, states of matter. We define temperature as the average kinetic energy of particles in a substance. Okay, so if I'm increasing temperature, I'm increasing the kinetic energy of the particles, meaning they're moving more and they're going to come in contact with other particles more. And that's going to make it, again, bringing that fresh solvent around the solute, making them more likely to dissolve. Now, there is an exception here, and that's for gases dissolved in liquids. As temperature increases, the solubility of the gas does decrease. Now, this picture here is a solubility curve. It shows the amount of solute that a solvent can dissolve at different temperatures. And I kind of want to zoom in because this is going to be a really, really helpful diagram for us. And so I want you to really see it well. Okay, so on the x-axis, we typically have temperature as degrees Celsius. And then on the y-axis, we have solubility. And we're looking at the grams of solute per 100 grams of water in this case. But it could be in any type of solvent. In this case, we're looking at the solvent of water. And our different solutes are these different colored lines. So we're looking at dissolving potassium nitrate versus sodium chlorate versus potassium bromide versus sodium chloride. Okay? Now, here's some things we can see here. Look at 40 degrees Celsius. So at 40 degrees Celsius, which of these solutes will be the most soluble in 100 grams of water? We'll go up and see which one's the highest. It would be blue, sodium chlorate. You can dissolve, let's go over here. All right, if this middle line here is 100, because that's halfway between 80 and 120, if I'm going over here, I'm between 100 and 120. So you can dissolve about 110 grams of sodium chlorate in 100 grams of water at 40 degrees Celsius. Now, if I increase the temperature, say to 80 degrees Celsius, look how much more I can dissolve. I can dissolve 160 grams of sodium chlorate. Also, look, potassium nitrate has the same solubility at 80 degrees Celsius. It's more soluble above that. It's less soluble at lower temperatures, but at 80 degrees Celsius, it has the same solubility as sodium chlorate. Okay, so these are the different kinds of things we can interpret from a solubility curve. Now, one more factor that affects solubility that I want to mention is pressure changes, but this only impacts gases dissolved in liquids. The higher the pressure, the more soluble the gas is. And this is due to Henry's law, which states the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas on the surface of the liquid. Okay, I just want to mention that very briefly, especially because we covered gases so much in our last concept, our last unit, 7 states of matter. Okay, one last thing before we start practicing interpreting those solubility curves is another way you can describe the types of solutions is based on their saturation. Okay, so a saturated solution is a solution containing the maximum amount of dissolved solute at a given temperature. It's as much as it can hold at that temperature. Okay, if I'm going to dissolve the solute, it's going to mix in uniformly and perfectly here. Now, a supersaturated solution has more dissolved solute than it can actually hold at that temperature. Okay, it's above its max capacity. So if a solution is already saturated and I add more solute to it, it's just going to start pooling up at the bottom because it cannot dissolve anymore. An unsaturated solution goes the other direction. It has less dissolved solute than it can hold. It's below its max capacity, so it could take on more. You could still dissolve more to it. And we can use these terms when we're looking at these solubility curves. Okay, so looking at this solubility curve, okay, let's look at potassium bromide at 60 degrees Celsius. The saturated level of potassium bromide at 60 degrees Celsius is 80 grams of it in 100 grams of water. So at 60 degrees Celsius, you can hold 80 grams of potassium bromide in 100 grams of water. If you add 100 grams, it's going to be a supersaturated solution because that's above its max capacity. If you put only 60 grams in, it's going to be an unsaturated solution because it can still hold more. Again, this depends on temperature. As the temperature is raised, that saturation level is raised and you can add more to it. Okay? We're going to practice this again with some practice questions looking at solubility curves, and I think it'll make a lot more sense there. So that is concept 1, types of solutions.